Hello, my name is Dr. Brock Lundberg, and I'm Fiberstar's Division President of R&D and Applications. In this module, I'll be talking about citri-fi's natural ability to form stable emulsions by binding both water and oil. Citri-fi starts as a byproduct from a citrus juice plant. Here's a cross-section image of an orange and its many fibrous components. Some of these components are what's gone in to make citri-fi. Before processing, the fiber structure is very smooth and compact and would have a very low water binding and emulsion property. After processing, the fiber structure is opened and expanded to create a high surface area. The expanded surface area significantly increases the contact points to improve porosity, as well as hydrogen bonding and hydrophobic interactions to stabilize both water and oil emulsions. Citri-fi contains 75 to 80% fiber depending on the product. The product is about half soluble fiber and half insoluble fiber. The soluble fiber attracts water as well as oil, and it helps to provide viscosity. The insoluble fiber provides structure and stability. The protein helps to actually bind fat and oil due to hydrophobic interactions to form more stable emulsions. These benefits and properties are unique because there's very few ingredients in the marketplace that are able to bind both water and oil naturally, even during adverse conditions. Citri-fi is able to form emulsions as a result of the physical and chemical mechanisms. Citri-fi's surface area physically entraps and holds high levels of oil. In addition, the native pectin and protein attach to the oil droplets to create emulsions and stability. This activity is illustrated in the schematic here, where anchor points hold the pectin to the oil droplets to create a loop and tail effect. The positively charged protein interacts with the negatively charged carbohydrates to absorb pectin and oil droplets. The pectin chains are attached to anchor points on one end, which absorbs the oil-water interface, while the hydrophobic tail extends into the aqueous solution. Citri-fi's pectin, in combination with the other biopolymers, create a layer-by-layer emulsification effect. The oppositely charged polymers create layers over the oil droplets to completely encapsulate it. Another advantage of having HM pectin and cellulose in Citri-fi is that the hydrophobic groups help to break up the oil droplets to form stable emulsions and associate with the insoluble fiber. We'll be able to see this on the next chart showing the fluorescent micrographs. Here's a micrograph of hydrated Citri-fi plus water and oil. The green color is the insoluble fiber. The blue is the insoluble fiber containing pectin, and the red is the oil droplets. This is an emulsion that we formed using the same demos that we'll show on the next slides, but the insoluble fiber is trapping the oil, which is shown in red, and the soluble fiber helps to glue the components together and form a uniform mass. This is an emulsification demonstration that we commonly do to show off the emulsification stability. Citri-fi will hold 2.5 to 3 times its weight in oil. And this is a unique feature of a natural fiber, since most other emulsifiers are chemically modified or high cost. In this demo, 5 grams of Citri-fi 140 are added to 15 milliliters of vegetable oil. The mixture is stirred for a few seconds, and then water is added. At first, the solution will have really low viscosity. As the water is added and the solution is mixed, the solution will begin to swell to create viscosity and a stable emulsion. The previous demo was a quick way to show how the emulsion formed, but we'll take another look here, where water and oil are dyed, and the mixture stirred to form a similar emulsion with the similar ratios described before. The bound oil and oil droplets are poured into the water here, dyed blue, and during the mixing, you can see as they break up in size and the fiber begins to bind the water and the oil. The hydration is complete once the emulsion is formed and a green paste that's now thick and viscous. As we pour this out, you'll see that the viscosity is generated relatively quickly and will be stable for a long period of time. A study was done here that will show the optimal level of citri-fi to use to form different emulsions. In this study, a 50-50 ratio of water to oil was used to understand the amount of citri-fi that's needed to create a stable emulsion. Here, 3% citri-fi was used and to find an optimal emulsion. However, less than 3% citri-fi can still be used to form stability, but there's some separation that occurs over time. But still, the citri-fi does still keep binding the oil. This study actually reflects why it's common for food manufacturers to use other stabilizers or thickeners along with citri-fi to form long-term stability and suspension, because the citri-fi is effective at binding the oil, but to avoid separation over a long period of time, another suspending agent or thickener may be needed. Another study was done to see how citri-fi 140 could emulsify at different water and oil ratios. We also evaluated the results after 3 days to see the stability over time. After 3 days, citri-fi stabled up to 4 parts water to 6 parts oil. This optimization gives manufacturers a starting point to see how much water and oil can be used when formulating with citri-fi. Citri-fi's natural emulsification properties have benefits in many food applications, and we'll cover a few of those in upcoming training modules where we're going to cover beverages, sauces, dressing, meats, and even bakery products. In this experiment, water and oil emulsions were prepared starting at ratios of 50-50 and various levels of citri-fi 140. The top chart shows citri-fi ranging from 1 to 5%, and citri-fi is partially ionized when going into an aqueous phase, which actually generates conductivity. The conductivity linearly increases when more citri-fi is added. In the experiment on the bottom, oil and water emulsions were also prepared by varying ratios, starting from 8-2 to 2-8. The conductivity decreased as the water level decreases, and conductivity drops while it's in the continuous phase until the emulsion inverts to a water and oil. As shown in the chart, the emulsion inverts to oil and water at a point of about 3-7. When the water level is 3 and the oil level is 7, or when the water, or up to 2-8, oil becomes the continuous phase. Because oil doesn't have conductivity, this is a sign of the change in the continuous phase, and thus the solution inverts from water and oil to oil and water. Because citri-fi uses physical and chemical mechanisms to create emulsions, a typical HLB effect or test cannot be used to measure emulsification. To understand how effective citri-fi and other emulsifiers work in the marketplace, we actually created a test to quantify emulsification and oil binding capabilities. And these results are actually shown here is the Emulsification Stability Index, which measures the amount of oil that can be bound by each gram of stabilizer or citri-fi. The test involved mixing the emulsions up with water and oil and then centrifuging off the water and the oil to see how much remained bound. In other words, if the ESI or the Emulsification Stability Index was 8, it shows that the citri-fi is able to bind 8 times its weight in oil. Other ingredients that we tested here include oat fiber, lecithin, carrot fiber, and citri-fi is able to bind 5 to 8 times more compared to the fiber, the oat fiber, or 2 to 3 times more oil compared to lecithin. As discussed in previous modules, citri-fi's fibrous matrix opens up even more when exposed to high shear. The expanded and sheared fiber will not only hold more water, but oil as well. Here we compared an emulsion texture when mixed by hand versus 2 higher levels of shear when using a high-pressure homogenizer. The increased shear will cause the emulsion to thicken, and increased pressure reduces oil droplets even further to enhance the water binding and oil binding properties of citri-fi. Because many ingredients will break down with shear, this is a unique feature of citri-fi, and it will help preserve food quality over time without chemical modifications. This concludes the module about emulsification, and the key point about citri-fi is that citri-fi will help form stability and bind oil even under adverse conditions. The mechanism is a physical and chemical, resulting in a natural emulsification properties when citri-fi is added. Citri-fi can be labeled as citrus flower, dried citrus pulp, or citrus fiber, and can be used to emulsify high levels of oil, and can be used in a wide variety of food and beverage systems. Compared to other ingredients, citri-fi provides stability over time and through a wide range of conditions of pH, temperature. And lastly, citri-fi generates more functionality when composed to shear, and other ingredients tend to be sensitive to shear, whereas citri-fi actually is improved with shear and can provide natural stability for food manufacturers. Thank you for watching this emulsification module. If you have any questions about the topics that were covered or need technical support, please contact any of the people shown on this contact page.